I wanted to talk about three different uses of feedback control for proposed management of uncertain populations. There are way more slides here than could possibly be covered in the amount of time allotted. I'm not going to try to rush through things. I'll just wind up skipping stuff as needed. So this is all theoretical. None of this has been tried in the field. But it seems that this seems pretty sensible. Now, when I'm saying feedback control theory, if there are any biologists out there or population managers, the phrase is adaptive management, and it's not. Pardon me? Oh. And it's not that it's not that they use control theory, but when you're monitoring the system and using those measurements in order to inform what you're going to do, that can be called adaptive management. So for conservation, control can be used to determine how to replant or restock. And for management of invasive species, control can be used to determine applications of pesticide or biological control. And the goal in these two types of problems, the control measures should be implemented with only access to specified limited observations of the population. So you're not assuming you can see everything or measure everything, and in a manner that is both independent of the initial population distribution and robust to model certainty, measurement errors and disturbances. So we're assuming there's a lot of uncertainty in the system, which is a pretty sensible assumption for a lot of biological systems. In open loop control, the control is determined at the initial time based on your knowledge of the model. An example of this would be Pontryagin-based optimal control, which has been used in ecology and population management, and University of Tennessee is an especially good place for this type of work. In closed-loop control, the control is a feedback of an observation of a system. Such techniques as integral tracking, we're going to talk about these, adaptive control, and observers are common in engineering, but have not, to our knowledge, been used in population management. There's a little bit that I've seen, but very little. And obvious question is, which is better? And the only answer you could possibly give to a question like that is it depends. If the model for the system is accurate, open loop control will be very effective. However, open loop control typically has little or no robustness, so the control might not be effective if there is model uncertainty or drift over time. Most ecological models are uncertain and subject to disturbances and observation errors, so open loop control might wind up being ineffective. Feedback control requires frequent monitoring of at least part of the system. That could be a deal breaker right there. Also, feedback control does not typically minimize the costs. It is optimal control is optimal. Feedback control most definitely is not. Feedback, however, is typically robust in the presence of uncertainties in the model and without precise knowledge of the system parameters. So this is, in control theory, this is kind of known as a trade-off between performance, optimizing a cost, minimizing a cost, and robustness. Now, this just kind of makes sense intuitively that the more robust you want something to be, the more general it is, and the less it can be tailored to the specific situation in order to try to optimize things. If the uncontrolled population is endangered, the control still has to be continued to be applied, although that's not specifically a closed-loop issue. This is an issue with any control where the uncontrolled population is in decline and you're constantly having to push it up. I'll say more about that a little later. Okay. Now, the kind of models we're going to look at, I'm not going to spend too much time on it because I'm guessing that in this audience, people will know a fair amount about this. Stage-structured population models. Individuals are partitioned into demographically different stage classes. For instance, there's natural divided insect population into egg, larva, pupa, and adult stages. For many plants, the stages can be better described as a continuous function, such as stem diameter or some other indicator of size. Matrix models are used for finally many stage classes, and that's what most people are familiar with, but I'm seeing more and more integral projection models used for a continuum of stages. In this talk, we'll consider models which can be of either type, just because now there are integral models, integral difference models. By the way, everything I'm doing is going to be discrete time here, although it can be adaptive for continuous time. But the biologists I work with like discrete time better. There are very complicated integral difference models, but they're not of this form. These integral projection models act a lot like matrix models. To get a little mathematical for a moment, it's because those models, the operators for those projection operators are compact. But we don't need to know any of that for this. So there's a state space. So the population vector at time t, x of t lives in the state space for all time. So this is a very standard for discrete time models. For example, if there are finitely many stages, x is equal to Rn, and that's what you're going to be used to for matrix models. A continuum of stages, x is going to be L1 of S, where S is the set of stages. Okay. For models, if you actually had spatial spread, then the state space gets more complicated. We're not going to worry about that today. Okay. Let's do it. We're going to do it linear. It's easier to explain stuff linear. All this stuff has nonlinear counterparts, but it gets more complicated, and most of the sort of general statements I'm making have to be qualified quite a bit for nonlinear systems. Okay, so we have a standard discrete time system. Does this thing have a, oh, here we go. Standard discrete time system, and t is a fixed unit of time, month, year, week, season, and thus t is just going to be 0, 1, 2, etc. For conservation, so for conservation questions, we're going to be assuming that the population is in decline. And for eradication problems, we're going to be assuming that the population is increasing. It's this issue here I want to bring about. It's the largest eigenvalue, or the largest modulus of an eigenvalue of A. If that's less than 1, then the population is in decline. Again, stuff that most of you probably know. Here. Okay, so now we've got our system. We're going to put in two things. Going to put in a control. I'm thinking of this as a control vector, one-dimensional vector. I didn't write this down, but with a one-dimensional control. Everything here can be done with a lot more generality, but it just messes up notation. At one point, I'm willing to mess up the notation, but most of the time, I'm just going to be leaving it and this. And then we have the observation. So here's the state, and the observation is part of the state. Let me go to the next slide. For population dynamics, the observation may correspond to a census or survey data. This can specify which stages are monitored. Here, C sub t is a functional, you can think of as a row vector, which picks out the stages or weighted sums of the stages from x of t. Okay, now for endangered species, U of t might correspond to introducing members of the population from planting or a captive breeding scheme. Here, B will represent which stages the new members are introduced. And for invasive species, U might correspond to an amount of pesticide or biological control applied to part of the population. And here, B will represent which stages are suppressed by the pesticide. So I'm just going to go back again. The B here then says what stages, what parts of the system U acts on. Okay, so now we're going to start talking about the first type of feedback model I want to consider. Integral tracking for conservation. Okay, so regulation and management to a constant set point is a fundamental goal in engineering and in science in general. In conservation management or pest control, managers would aim to regulate the population to some desired safe density. And so at this point, so the first two topics I talk about are going to be published already. And then the second two the third topic is going to be work in progress. And this one is in a 2014 publication. The internal model principle, that's something in control design, implies that if one wants to track constants, the controller needs to be of a very specific form called an integral controller. The term integral controller is, I'm going to try to motivate that word, but it's going to be a little hard to do here. A striking feature of integral controllers, or in general, PID controllers, proportional integral derivative controllers. So these are kind of bread and butter engineering techniques. In general, controllers in general, is that they can be implemented on the basis of very low knowledge of the system to be regulated and in the presence of considerable system uncertainty. Now, a particular reasonable management goal for the observation, so let's suppose you're just observing adults of the species, or reproducing plants or something like that. A reasonable management goal would be to converge to some pre-specified reference value as t goes to infinity. For now, we'll think about it in endangered species. I guess I said this already. So that the spectral radius of the uncontrolled system is less than 1, so the system's going to decay otherwise. Okay, let's start with the simplest idea. No feedback. Just restock by constant predetermined amount each time step. And I didn't say what g of 1 is. It doesn't really matter for our purposes. There is a constant that we can put in that will lead to this. And it's really easy. And so the question would be, well, why would you do anything else? Because this has got to be easy to implement. This is very non-robust. I'll show you why. That is, if we perturb the model parameters, this control will lead to very different limiting behavior for y of t. Okay. So the other problem about this is we need to know A, B, and C. It didn't look like it, but that G of 1 thing had A, B, and C in there, which we might not have access to. Okay, so here is the numerical simulations we've done on this very simple thing. A declining wild boar population, and this is what we want to control to. But instead, and this is what it does without the control, right here. Okay, now the reason there are 3 for each, what we did is we randomly perturbed the model parameters, not very much, but then put in the control that was intended for the nominal model parameters. This is just from the literature. I'd be terrified if I ever saw a real wild boar. We just took an example from the literature here. So this is not a pressing need to. So this is just as an example of things. So I was actually unaware of that. Okay, so measurements. Okay, so what we want to do is hit this. You could also track to a lower population, although there are better feedbacks to do that. And then measurements of, okay, the adult female boar are with the control are in here. And so what happens, you're trying to hit this, but if you were off slightly and put in the same control, you could hit wildly different things than you wanted to. And with those same randomly perturbed things, you're still getting the decay. So this kind of control is extremely unrobust. The lack of robustness is typical of open loop control in general. Feedback control is more robust since it reacts to the system at each time step. In a typical application, the feedback control is chosen as a function of the observation and not as the whole state. So I've been kind of hitting that point so you don't have to measure the whole thing. As it is, monitoring even part of the system could be prohibitive, and certainly monitoring the whole system would be prohibitive. And then we consider the following very simple controller. The control at time t plus 1 is this last control corrected by the difference between where you are and where you want to be. And this k is a gain parameter. And choosing the k properly is a bit more of an art form than a science. I'll talk about this in a moment. Now, the reason it's called, this next part is here just as to try to convince people this is called an integral controller because when these accumulate over time, u of t looks like this. And this is a discrete time integration of the error. So that's why it's called an integral controller. It's a little more convincing in continuous time. Okay. Now, this type of dynamic controller, so it's not just a feedback. It changes with time, and it can generate feedbacks that a static controller like this cannot. And again, I'm talking about the internal model principle. It's not something that we should be worried about in this talk. But for control theory, it's a pretty important thing to keep in mind. Couple these together to get a closed loop system. What's good about this? We only need the observation to implement it. It's robust with respect to parameter uncertainty in the model. We'll be showing that. What's not so good about this? There's no optimization, and it really is very far from optimal in many cases. It requires frequent monitoring, as I mentioned before, which could be a deal breaker. And this is not so much, again, about this. It requires continual control to keep the population up. Because if the system without control is decaying, to keep the population up, you're going to either have to keep on doing it or keep on doing it until you've somehow done some additional conservation efforts, change the life history parameters or change the environment so the system isn't in decline. This is not a long-term solution to anything.
Is that the case for nonlinear?
It gets much more complicated in nonlinear, but if you have a nonlinear system which is in constant decline, you're going to have to keep on doing something or change it, or change the system in more dramatic ways. Oh, static because it just says do the same thing every time. Yeah, but you're taking your observation, you're multiplying it by the same thing every time.
Oh, okay. I see. But you weren't on the previous summation multiplication.
Okay, let me go back because I might be conflating the next method. Let me take a look here. Okay, so here there's a dynamical system. Well, yeah, we have the K, but the difference here is that you have a dynamical system for it as it is. Okay, it's a very boring dynamical system, but then you're throwing stuff in. So so the difference is you need a.
It's like it takes the history to get the next.
Exactly.
I got it. Okay.
Exactly. Okay, so let's see, what's not good about it? Okay, so now integral control applied to the possibly fictitious declining wild boar population, each with randomly perturbed model parameters. So you see here that the idea here is now, once again, to get to 500, and we're doing the same random perturbations of the model parameters that we did in the open loop constant control. But now, because we're monitoring and we're constantly correcting, we're able to get some pretty good robustness. If some of them take longer to get where you want than others. I mean, this 60 years is an awful long time to wait for these things, but it is pretty robust. And let's see. Now, here's a theorem. The theorem saying these words aren't going to help that much. So let me just say, if you do what we just said, then there's a mathematical theorem that guarantees that you're going to, the one that our goal was to do this, but when we do this, the whole state converges to this. This is the state you're stuck with if the observation does this. And the control will converge to that thing that we said was the good constant control, but that wasn't very robust. No, G is very easy. It's a transfer function. It's if you don't know the model parameters, you can estimate it using sort of input-output techniques. No, we're not. We don't need to know very much. We don't need to know the parameter. That's just it. We don't need to know the parameters. The control itself. So here's what's going on. The one thing I didn't say that some of you would appreciate is that we need controllability and observability here. If we don't have that, then this is not going to happen. And I guess I didn't. Just look. Okay, so yeah, so G is just a transfer function, but the thing is, you really don't need to. This is not what you need to know. What you're trying to do is this, and you don't need to know very much about the system. You need G of 1 to be greater than 0, and you need control and observation. I think somewhere I might have those conditions. Okay. In particular, a closed-loop observation does indeed track R. We can prove, that the control is robust with respect to perturbations of A, B, and C. Okay. Now, the theory. I'm going to slip over this, but there's one really cool slide that I want to get to. The theory ensures that an upper bound for K exists, which we usually call K star. This is called, so the theorem says for sufficiently small K. Now, how do you find K? We have estimates of K star, the sort of how high you want to do it, if we know A, B, and C, but nothing that's guaranteed to be sharp. We have lower estimates for K star, which will guarantee convergence. Now, the gain parameter K is a very important role in control strategy. Loosely speaking, it's a tuning parameter. Larger values of K give rise to faster convergence, but too large a value of K can destabilize the system and destroy convergence. So root locus methods are usually used to determine good values of K. So that's something you would learn in a control course, perhaps in an engineering school more than a math department. For faster convergence, one can add proportional control. Let's skip this. Okay, wild boar, again, we assume that the initial population distribution is random but has total density 1. I think this is more of an example here. I think I made my point. Yeah. I'm going to skip that. Here's the cool slide I want to get to. This is for different values of K. And unfortunately, it's not in color. It should be in color. But the idea here is that for K is equal to 0.6, the population does not converge. You get for K is equal to 0.4 and 0.2. You're going to get, in 0.2 you get good convergence. 0.4 you're getting not as good. I should have shown some slightly smaller ones, which were going to be less good. But then K is equal to 0.6. All hell breaks loose, and in fact, the population even goes below 0. So the model breaks down completely. The control scheme breaks down completely. So the moral here is just that the gain parameter is something that you usually do by trial and error. There are ways of getting it, but they're fairly difficult, and it's easier to simulate. Right, the gain parameter, okay, so it's how much, you take your error and then you weight it by the gain parameter. So the idea is if you're a little high, you push it down a little bit, and how much you push it down depends upon the gain parameter. But if the gain parameter is too high, you're just going to be chattering, and if it gets really high, it's going to be going crazy. So same kind of thing here. Now, there's other things you can do, and I'm looking at the time. I think this would be good stuff to skip. Basic idea, when you're doing this, you might not want the control to get too big or too small. For instance, you never want the control to be negative, and yet sometimes the tracking might tell you that the control should be negative. But you don't want to kill your endangered species, so sometimes you will filter the control. So you don't want that to happen, and then there's sometimes limitations on how large the control can be. So you can fix that, and you can now have a control which doesn't let you get above some upper bound that doesn't get you below 0, so you're not killing off the endangered population. And let's see, and then we did an example, and it still works. Okay, so, oh, and this is pretty cool. You can choose the K adaptively. You can give K its own dynamical system. So now you've got here so H satisfies this dynamical system. Okay, this is a weird thing. And so you put that into the system, and then you put 1 over H in for K. And this tracks every R greater than 0 and every A, B, and C such that rho of A is less than 1 and G of A is greater than 0. It is extremely robust, and it does not require very much information. So this is called a universal adaptive control. A lot of people use it. It does not converge very fast at all. It's a very inefficient thing to do. But people use it when you have very little information. You can use it. So we can do it for integral projection models. We can do it for some models with spatial components. We can incorporate some nonlinearities. This is just talking about the kind of system. Again, don't want to talk about this that much. I don't want to talk anymore about the nonlinear case. It starts getting mathematically technical, but you get the same kind of results. But there's some mathematically interesting things going on there. You can prove that it is robust. So you put the disturbances in, and you can prove that it's robust. So let's see. There we go. I wanted to switch now to a different topic. It's still feedback control, but it's a different type of feedback control. So Tom Miller and Brigitte ten Humberg. Brigitte is Christina's co-advisor, gave a state structural dispersal model for spread of an invasive root weevil, an herbivore that has invaded and continues to invade citrus-growing regions in the U.S. So if you've gone to some of Christina's talks, she's talked about the optimal control of this. In the paper, X of t is 6-dimensional. We work with a 3-dimensional version. Just makes it a little easier. And let's see, and it's just back where we were before. And the projection matrix now has an eigenvalue that's greater than 1. So in the absence of control, the population is growing. So we want to do something about that. Simple adaptive control. So this is the paper that this work appeared in. And we envision using nematodes, small worms that kill the host, which is a pest insect larva. And they're used instead of pesticides and are proved to work very effectively. So we assume that the hosts are distributed according to a Poisson's misspelled distribution. Then assuming nematode attacks are random independent, you can show that the probability of a host not being attacked is this, where alpha is a search efficiency and U is the nematode numbers. The same principle applies to, if we're going to do insecticide, the probability of surviving a chemical application is the same kind of thing. So we're looking at things like this, decay like this. Let U be the control, nematode or insecticide, which represents how much should be applied at each time step. So this term is 0 when no control is applied, but saturates to 1 as the amount of control goes to infinity. This is saying that increasing control will have decreasing marginal effect, which makes sense. Okay. Once again, the vector B is telling you which stages the control is applied to. And this depends upon the different types of control, because pesticides might act on different stages than the nematodes might. The control is more effective if there are more weevils available to kill, so we're putting a bit of this in here. So the effect of the control is proportional to, you have a row vector which picks out the part of the state that makes this a true statement. So it's just a little more generality. So then the control system we have is this. Okay. This is packaged a little differently than Christina's been looking at it, but it's pretty much the same model. And we're trying to choose the control U of t. So Christina's done the optimal control of this. Now, more generally, on this one, we decided to do it as, to abstract the hell out of it. But it's basically the same idea here. And so now we have this abstract thing. Let me get to the interesting stuff. So the control is targeted at only specific life stages, which says something about B. Okay, invasive, so we're assuming that it grows in the absence of control. We assume for large enough to control, the population will decline. Okay, so what's going on here is that there's that as we keep on putting on control, as we put control in here, so we have this, as we put control in here, eventually it's going to hit an amount which is enough to push the population into decline. We don't know where that is. We usually don't have, we're not assuming we have enough information on A, B, and F. By the way, we do know phi, but we are assuming we don't necessarily know enough about A, B, and F to say exactly what it is, but we're assuming that there's a certain amount of pesticide that can do the job. This suggests that we want to do a high gain control. The other one was low gain, trying to do as little as possible. Here we're going to do a high gain control to apply enough pesticide or biological control. Now, the conditions for high gain control, there's a large literature on this, but it's really inaccessible to biologists, and it typically requires more information than we would have. These phrases like minimum phase, relative degree, minimum realization, knowledge of high gain response. The first three of these are typically not known for a population and system. But what we often do know is that this system is irreducible, which might come from the life history transitions. So that's the kind of thing that a life history diagram would probably tell us. That's the kind of thing we would know. We know a lot about A, F, and phi, and it's generally not possible to find a fixed control so that this does the job, unless we know a lot about A, F, and phi. So we're going to assume we don't, again, because these things we're assuming are very uncertain. Otherwise, we'd probably do things optimally. However, under some easily checked conditions, we can prove that the gain can be chosen adaptively. Okay. So we have an observation which picks out what we're actually going to base the control on. So if we can only see adults, that says when we apply this to x of t, the third, so it's going to be 0 of the first, 0 of the second, and 1 of the third adult stage. And we propose the following feedback, where this whole thing is a design function that we get to choose. Okay? Under some non-restrictive conditions, there exists that you can get the population to decay exponentially. So that's our theorem there. I don't think. Additional conditions guarantee that you will have a nice limiting control. And in addition to this, you will get, so these things to the trained eye might look pretty similar. They're not quite the same. So under additional conditions, you can get a slightly better result. So the idea is that instead of hunting and pecking for the right amount, which could take a long time because it's hard to simulate things if you don't know what the matrices are, you can use this high gain control and it will find it for you in some way that's not optimal but is robust. Okay. So for simulations, we only acted on the eggs, and then we we had this search efficiency here. We started our simulations. You have to start somewhere with you, because the control is the dynamical system itself, you have to start somewhere. So we started there, and then we chose 3 different choices for the design gain function. And the following plot shows the resulting states of the control. So it's actually not the states, it's the norm of the states, with adaptive high gain feedback. Note that even though the system without control is growing, the control drives the population to 0 in each case. Each time step is a week, so 100 time steps is roughly 2 years. Now, you're going to see here, you're going to get better results with, like this one gives a lot better results. Psi 3 gives a lot better results than Psi 2 or Psi 1. The graph shows the resulting control amounts here. And that's important because you don't want to use, I mean, if you're using pesticide, for instance, you don't want to use too much of it. The adaptive control finds a sufficiently high control amount without putting that large amount in all the time. The amount of control varies with the choice of psi. We see that the lower control effort corresponds to psi 2. We see that the lower control effort corresponding to psi 2 results in a smaller state norm than the larger control effort for psi 1. So psi 1, let's see, and psi 2. So you're putting in less control here, but if we go back, you're getting more decay here. So psi 2 is going to be a better one. Again, art form rather than, that engineers have become very good at, rather than an easy way, an easy theorem that'll tell us what is best to use. Robustness, it's very robust. This is the limiting control. I'm going to skip because, this is kind of interesting. You can, when the observation is larger than some set level, you have to put in more control to kill it off. When the observation is small enough, you can decrease the control using adaptation that's not built into there. And between these levels, you can just have a constant amount of control. You can also switch. If you can't control the pest with a proposed controller, you can try different strategies, and there are clever ways of doing that. So let's see, I'm just skipping along. Other approaches, changing the dominant eigenvalue corresponds to improving vital rates or quality of access to food, and that's what you want to. You don't want to keep on hitting the system with pesticide, or in the case of an invasive species, you would like to make some long-term changes. Markov decision process, partially observable Markov decision process, stochastic dynamic programming. There are all sorts of stochastic ways of doing this. I don't know that much about it. These are methods which manage optimally, and typically they're computationally intensive for high-dimensional models. And then I mentioned before adaptive management. It's a management term that changes the management based on the results of monitoring. Okay. This is the new stuff, which I wanted to spend a little more time on than I'm going to. But, so, you reset your mind, we're going to do something different. We have access to the observation. Now, our goal is we want to know the whole state. Suppose we can, there are some stages we can measure, but some stages that we can't. A seed bank, for instance, we can't ever see. Or an animal that reproduces in seclusion. As an example, we're going to consider a biennial monocopic plant with seed bank vegetative state and flowering state. Population vector is going to be the density or amount in the seed bank, density or amount in the vegetative plants, density or amount of flowering plants. And you have a nice, simple population projection matrix. The observation of the system, what can we see here? What can we count? Well, we're not going to be able to count the seed bank, but we can count the vegetative plants and the flowering plants. And so what this says is we're going to, hey, we get to see the vegetative plants and we get to see the flowering plants. We get to see both of them. The system is observable. Now, I'm not making a big deal about this, but I probably should. I'm not doing it in this slide. That is, one can uniquely determine the states from the observations. So observability is important. If the system isn't observable, there's nothing you can do. Now, as an aside, it's actually pretty hard to come up with a simple matrix model for a sensible population where you don't have some observability. Here is a matrix model which doesn't make any sense for a system because it's just going to be two populations, and one is going to have its survival rate and the other is going to have its survival rate. No connection between them. So I just want to give an idea of what kind of things aren't observable. Well, if you just observe this, you're never going to get this. If you just observe this, you're never going to get this. I didn't write that, but that's pretty easy to see. What if you observe the sum of those? The system turns out to be observable unless S1 and S2 are the same. If S1 and S2 are the same, if the survival rates are the same, knowing X1 of T and X2 of T will never allow us to separate out these. Where if you have different survival rates and you know what the survival rates are, then you can separate them out. So these observers can only work if the system is observable. And this is work in progress, but we feel like a lot of the results we get are going to be able to be explained in the context of observability. We're not there yet, though. So a general dynamic controller where the observation is fed into the controller. So here's what is called in terrible terminology for us here, the plant. It has nothing to do, it's the system you want to control. X of t plus 1 is ax of t plus bu. Y is equal to cx of t. So it's controlled, observed. Then you construct another thing here, and this y really should have a sub c next to it. And it's the controller. It's another system that you're allowed to construct offline. So you construct in the computer. To solve problem 1, we want to choose. So problem 1 is to go from your observation to the whole state. We want to choose A sub c, B sub c, C sub c, so that X sub c is asymptotic to X. That is, the control system reconstructs X. In this case, the controller is called an observer. So this is something which will take your output. I really want to go back here because just to see, you take your output. Oops, sorry about that. So what you're going to do, you're going to take your output here, and you're going to feed it back into here, and then you're going to take your output from here and feed it back into here. So you close the loop in two ways, and the system, if you choose those things right, this is a classical observer, and unfortunately, as I said, work in progress. First time I'm doing these slides. I should have shown the two feedback loops, but you're putting the output from one into the input of the other, and you're doing that twice. And then under certain circumstances on the matrix H, you can get that the controller approaches, which you have access to, approaches X of t. So observers can also be used, and we're going to show this a little bit. Observers can also be used to update parameters. If you're unsure about your parameters, you can use your observations and feed them back in and update your parameters to get better and better parameters. Okay. Now there's something called the Kalman Filter, which is an optimal observer, but optimal in a sense that has nothing to do with the optimal we've been talking about earlier. I'll have to explain what that means. So we're assuming a nice simple system here, but we're now assuming some noise, where mu and w are zero mean Gaussian white noise. Now, you might have that. That's kind of hard to tell whether you have that or not with known covariances Q and R. Are you really going to know that? Probably not. It turns out, however, that the Kalman filter still works well in the absence of these things. but we can also do something to update this information, again, using the observations. So noisy system, noisy observation. Problem 2 is to estimate the noisy observation given, estimate the noisy population given the noisy observations, y of t. This can be solved by a Kalman filter. It gives an estimate, x hat of x of t, that is a conditional expectation of x of t given the observations. Okay. Now, a little bit of description. This late in the talk, trying to understand something complicated might be a fool's errand, but if x of t is a set of all possible estimates, x bar, and that's not mean. This actually turns out to be standard notation in the Kalman filter literature, which surprises me because it's not mean. It's possible estimates given this information, and then you choose one, and you look at this error, which is a random vector, and suppose this error has mean 0, which it will under those circumstances. Then, since the covariance of this difference is a measure of the spread of the data away from this, of the mean, which is 0, choosing this expectation to minimize the covariance of the error means that we are confident that the error is as close to 0 as we can possibly be. So that's what we mean by observation. That's what we mean by optimal. That means that we have the best possible estimate given our observations. The Kalman filter then is an algorithm which takes observations and a variety of other things and outputs an estimate that minimizes the covariance of the error given the observations. It is optimally robust in that very specific sense. There are versions of the Kalman filter when the mean of the noise is not 0. Kalman filter can still work well when the estimates of the covariance are off and when the noise is not Gaussian. There are also Kalman filters for some nonlinear systems. Kalman filter, don't look at this. It's going to take too long. If we don't trust the life history parameters, so problem 3, use the noisy observations to update some of the life history parameters while estimating x of t. For this we use, and dual has nothing to do with adjoint here. The dual Kalman filter, dual has to do with what we think dual usually means. It's 2 of them. One Kalman filter to update the parameters, coupled with another Kalman filter to estimate x. We don't know a, so we replace a with a of t, and we have this new system which we're using to keep our information. We keep track of our information in this system where w of t replaces x of t as the population vector, and we reserve x of t for the original system. And then are we going to, the Kalman filter for the population now, so you have the Kalman filter for the population, which I didn't let you see anyway, so this you don't need to see this last thing. And we turn the parameters into their own vector, and we model the parameters as a random walk because they're noisy parameters. And then we get this observation of the parameters as d of t, which is really mysterious. So I'm not going to bother explaining it at this point. It's actually doable, but it takes way more time than I have. So now we have this other Kalman filter. I didn't want you to look at that one. I don't want you to look at this one. So go back to, because we're really pretty close to time. And I want to show the simulations. By the way, I should say most of this work was done by my graduate student, Nathan Popelreiter. He's the one really who's behind all of this. He's working on his PhD. He's going to most likely finish next year. And so we put in the parameters for a Eurasian thistle. And so we're assuming we can count the vegetative and flowering stages, and we want to somehow figure out what the seeds are. We have observations, albeit inaccurate. Everything in sight here is noisy, of F321 and S22 at each time step. And to observe S22, one might mark in 1 year, that's the survival from stage 2 to stage 2, which thistles are vegetative, and count how many of these thistles are still alive but not flowering the next year. So this is not unreasonable. It is reasonable to have an observation of F31 because we can estimate the probability of a newly produced seed germinating after 1 year, as well as the average number of seeds produced by a flowering plant. So we're going to estimate x of t. Okay, so our job is to estimate this. In lieu of using data from the field for observations, we're going to have yet another system which is going to be generating data, which we're going to act like is reality. So that third system is going to be in lieu of collecting data. Because if we want to do this, we're going to only do 20 time steps because 20 time steps is actually quite a bit for real data. We're going to see the estimate for S12 is terrible. We don't know why. This thing is our estimated x and our real x. And for I is equal to 2 and 3, it's for the vegetative state and the flowering state, it's pretty quick, and it's slower for the seed bank. This is because the vegetative and flowering populations are part of the observation and the seed bank is not. So if you're observing it, you should be able to do better. So really, we're updating everything at every time step. And all the updates are informing the other updates. The estimate for F31 oscillates around the real value. This is because of the relatively large process noise covariance. And now we just have pictures. This is oscillating, but it's at least somewhere around there. The error doesn't look too bad. Converging pretty well. This is the one I said was terrible. Yeah. No, that wasn't the one I said is terrible because actually it's not too bad here. But we don't know why, I gave some explanations, but this is work in progress. We don't know exactly why some of these things are better than others. This one's really good. This is the terrible one because it seems to be converging to something very far removed from what it actually should be. It's not even oscillating around it. It's just, that's the really terrible one. And this is a ratio. We want it to go to 1, which it appears to be doing. And another one we want to go to 1. And another one we want to go to 1. It's all doing that. So what we want to do now with this is explain why it is some of the estimates are really bad. We can try to do this using observability, but because these systems now are time varying, it has to be time varying observability, which is much more complicated to use. I think I'm going to stop here and open. Thank you.